Welcome to the next session on design of counters. In the last lecture we started with a small review of flip-flops and how to proceed with counter, design of counter. So that time we discussed a simple counter, a 2-bit counter that we discussed. Now in general we can go for designing any counter. So what would be specified to you? What a counter is expected to have? A counter is expected to have a clock input. A clock input. It is normally active low. So at the time of falling edge of the clock, counter advances to next state and few outputs as may be required. So if we go for designing a 4-bit counter, if you go for designing a 4-bit counter, it will be having outputs as Q3, Q2, Q1, Q0, or in some nomenclature you might also see that somewhere these are also called as either D, C, B, A. Means this convention is Q0 from LSB, Q0, Q1, Q2, Q3, or ALSB, A, B, C, D. And then what obviously the counter will change from 0, the counter will change from 0, 0, 0, 0, this is Q3, Q2, Q1, Q0, then 0, 0, 0, 1, 0, 0, 1, 0, and so on. So it will come to 1, 1, 1, 1. So in general we can construct, so simply what we are doing, count means in today's session we will cover all possible points of counter, that is up counter, down counter, a regular multi-bit n-bit counter, and then we'll also discuss very important point, that is a counter which doesn't advance to all possible states. So in general a counter is expected is, so this is called as a binary up counter. This is called as a binary up counter. In general, n-bit binary up counter. N-bit binary up counter. So I will explain to you very simple way of designing an n-bit binary up counter. I will write down all states and show you how we can go for. So this can be 4-bit counter. Last time we had considered 3-bit counter or 2-bit counter. Then I will say no, so why you are jumping to 4th bit? Okay, if you don't want to jump to 4th bit, I will just wipe out 4th bit. We will go for 3-bit counter, and then we can easily extend for multiple-bit counter. So if you want to design 3-bit counter, then I write the states Q2, so I add in outputs Q2, Q1, Q0. The states are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then you also write 0, 0, 0. So current next, like this. In this case then, how we go for designing it? In general, last time itself I have told you very clearly that we require as many flip-flops, as many number of outputs. So here this is a 3-bit up counter. A 3-bit up counter consists of 3 output pins. So each out in a counter, for each output you need to have 1 flip-flop. So 1 flip-flop, other flip-flop we can write down. There is no need that we should draw them either horizontally or vertically, that is not important. So all 3 flip-flops. So each flip-flop is having Q, Q bar, Q, Q bar, Q, Q bar, its outputs. These are local names inside, and externally there will be 3 pins coming out. So this I will name as say Q3, Q1, Q0. Q3, Q1, Q0. Each will have J, K, J, K, J, K. Each will have clock. Each will have clock. Then right now, if you go through syllabus, there are 2 types of counters, asynchronous and synchronous. That discussion was important few years back, few decades back, but nowadays that is not so important. Normally we use synchronous counters, but still as a point in the syllabus I will cover asynchronous counter. Synchronous counter means all flip-flops in that counter are driven by the same clock. So clock synchronous, ekach veli. So the clock of all is made common. Clock of all is made common, CLK. Each flip-flop is having J, K, Q bar, J, K, Q bar, and there is a master reset also. MR bar is there for each flip-flop, but right now we are not using it. When we are not using it, we are grounding it, or what we can have, MR of each master reset of each flip-flop. What master reset does? If this master reset is activated, if this master reset is made active, that is 0, then flip-flop all outputs become 0. So you can, this comes up as master reset of overall. This comes as overall clock. This comes as overall master reset. These are individual clocks. This is individual master reset. So this is fixed structure. Master reset of all is brought out. Master reset of all is brought out. Then each flip-flop's clock is made common, which is coming out as common clock, which we have to supply. Individual outputs are brought out, and they are named as Q3, Q1, Q0. So designing means what now? Designing means how we shall decide to give inputs J and K to these flip-flops such that the required operation is observed. So this I will call, when it JK, 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 for this flip-flop JK, for this flip-flop JK, for this flip-flop JK, but this is flip-flop number 3, sorry not Q3, flip-flop number 2, this is flip-flop number 1, and this is flip-flop number 0. These are flip-flop number 2, flip-flop number 1, and flip-flop number 0. So in this case now, this I will call, this J I will call bring out, and I will call it J0. This I will bring out and I will call as, sorry, J2, K2. This I will call as J1. This I will call as K1. This I will call as J0, and this I will call as K0. So what is to be done is now how the values J0, K0, J1, K1 and J2, K2 should be given so that this operation is observed on the outputs of these flip-flops. So what we want is, we simply want that the required operation should be observed on these outputs Q2, Q1, Q0. Now for this, I should simply go through the pattern of Q2, Q1, Q0. What is the pattern? I observe very clearly. Q0 is 0, 1, 1, 0, 0, 1, 1 0 0 1. So I find that in every next state, Q0 always toggles. The output Q of the flip-flop number 0, Q0 always toggles. So what input combination we have for always toggling? Now there is no need for me to cross connect everything. What I can do, I will prepare a table. Where what I will do, now I will simplify. Each time I will not connect gates and show you the diagram. Simply what I will do is, this is Q2, this is Q1, this is Q0. So what I want, what should be Z0, K0, what should be Z1, K1, and what should be Z2. So what should be Z0, K0, Z1, K1, and Z2, K2, that I will prepare. So what I should have? I find that flip-flop number 0 in the 3-bit counter always toggles. So when it always toggles, what kind of input combination gives me toggling output? Z equal to 1 and K equal to 1 gives me toggling output. I find here that in any case, current state, next state, current state, next state. So irrespective of other inputs or irrespective of other points Q2, Q1, etc., Q0 always toggles. Q0 always toggles. So I am not expected to consider anything else, and I should make Z0 as 1 and K0 as 1. I should make Z0 equal to 1 and K0 equal to 1 fixed. Why fixed? Because every time I find that the next state, means for all states of the 3-bit up counter, next state consists of the toggled output of bit number 0, Q0. So Q0 always toggles. So always toggling is ensured by me by making Z0 equal to 1 and K0 equal to 1, that I will type to VCC. This I will put to VCC, this I will put to VCC 1. Now, what we find, last time we discussed 2-bit counter is automatically, 2-bit counting sequence is automatically observed on the counting sequence of last two least significant bits of a 3-bit counter. So if I just cover up this row, then Q1, Q0 will be just like a 2-bit counter. So that also we discussed already. So what happens when, what about Q1? What about Q1? Q1 continues. It is 0, it continues 0. Q1 toggles. Q1 continues. Q1 toggles. So if I systematically observe, I find that the Q1 is either toggling or maintaining the state in an alternating manner. Alternating. Continuing, maintaining, inverting. Continuing, toggling. Continuing, toggling. Continuing, toggling. And what will happen? It happens on what was this next state of Q1. Whether it will continue or it will toggle depends upon current state of Q0. I hope you understand this now. Next state of Q1 depends on current state. Means if Q0 current state is 0, next state of Q1 remains same. If current state of Q0 is 0, next state of Q1 remains same. If current state of Q0 is 0, next state of Q1 remains same. And if current state of Q0 is 1, then Q1 toggles from 0 to 1. If current state of Q0 is 1, Q1 toggles. So, if Q0 is 0, the Q1, whether Q1 should be 0, Q0 is not deciding whether Q1 should become 1 or become 0. It is only indicating it should either maintain the state or toggle the state. So, what are the input combinations for continuation of state and toggling of state? If J and K are 0, 0, it maintains last state. If J and K are 1, 1, it toggles the state. So, for flip-flop number 1, I do not want any other input combination. I want input combination as 0, 0 or 1, 1. So, whatever is J is K, let it be 0 or let it be 1. So, what should happen now? When Q0 is 0, that time I want state to continue. So, J1 and K1 both are to be Q0 itself. So, if both are 0, so I will connect Q0 to J1 and K1. I am showing you by different color. I will connect Q0 to J1 and K1. J1 and K1 I will connect common and I will connect it to Q0. So, if Q0 is 0, they will be 0, 0 and this will continue. If Q0 is 1, J1, K1 will be 1, and when J1 and K1 are 1, 1, that time when next clock comes, this Q1 will toggle. So, Q0 is directly connected to J and K of flip-flop number 1. So, J1 equal to K1 equal to Q0. So, you short J1 and K1 and connect it to Q0. So, output of flip-flop number 0 is to be connected to common input of J and K are made common for flip-flop number 1. So, output of flip-flop number 0 is connected to common input of J and K of flip-flop number 1. I hope it is quite clear now. Then we go, so that was there in last lecture also, just I explained it in detail so that nobody should have any kind of difficulty in understanding. Now let us go for Q2. Let us go for Q2. So what happens with Q2? We find that Q2 normally doesn't change in most of the cases. So it is 0 continuing, 0 continuing, 0 continuing. Now toggling, continuing, toggling. So what kind of those who want to find the answer on their own, what should they do? They should put pause button for the video, think whether they can find the answer on their own. If they are able to find the answer on their own, it's well and good. They will verify the answer. If they are unable to find the answer, then they can again resume the video and watch. So those who want to pause the video now can pause the video. Okay. So what we find that continue, change. So in general, just by human psychology, suppose if that we find some leftist player, we immediately notice that. So we give our attention on the thing which is happening less number of times, occasionally and not normally. So what is occasional happening here? Occasional happening here is this, inverting. 0 to 1, 1 to 0. So that time, when Q2 is expected to invert, so we are designing So as obviously for flip-flop number 1, sorry, for least significant flip-flop like this flip-flop number 0, we directly toggle it every time, J and K we put 1. Then while deciding flip-flop number 1, we look at output of flip-flop number 0. Then obviously while deciding the flip-flop number 2, what we should do is we should look at other outputs, that is outputs of flip-flop number 1 and 0. And see now, this is something where human brain is having more powerful. There can be a systematic design, everything can be coded, and even you can make AI based system to think over it. But the power of human brain. So what you notice here, this is something which is a flash kind of observation and thinking. So 0 to 1 occurs, common feature I immediately notice that both are 1 1. And in other cases they are not 1. So that I instantly notice. Means flip-flop number 2 is expected to maintain the state, or rather I should use the thing happening less first. Flip-flop number 2 toggles when both other flip-flops, both lower end flip-flops Q1 and Q0 are 1, outputs are 1 1. And in all other cases it maintains the state. So if Q1 and Q0 are 1 1, then J2 and K2 should be 1 1. If any of them is 0, then J2 and K2 should both be 0. So if I and Q1 and Q0, if I have to put an AND gate, I should take it here. I should take it here. I should have an AND gate, and this I should so what is J2 and K2? I can write here as Q1 dot Q0. Q1 dot Q0. This is J2 and K2. So this is design of a multiple bit binary up counter. Now by same logic, you can design if Q3 comes, everything will remain same. For J3 and K3, you will be needing, J3 would be Q2 and Q1 and Q0. So when in case of a multiple bit up counter, the most significant bit changes when all least significant bits are 1 in previous state. So by this way, you can design any n bit counter. You can design any 8-bit up counter. You can design that. So this is the way with which we design up counter. Now we should design the down counter. What is down counter? Counter should reverse. Means it should go on this way, but I don't want to trouble you to think in a reverse manner. I will give you the appropriate sequence. So a 3-bit down counter, we start from 1 1 1, then next is 1 1 0, then 1 0 1, 1 0 0, 0 1 1, 0 1 0, 0 0 1. Oh sorry. 0 1 1, 0 1 0, 0 0 1, and then 0 0 0. So 1 2 3 4 5 6 7 8, and after that it goes back to 7. 1 1 1. This is a down counter. So its design is very easy, not all difficult. uh, those who want to design on their own should put a pause for some time, think how they can do that, and after they are able to finish up or they think that they are unable to proceed, then they can again resume. Now those who want to make a self attempt should put a pause, others should watch. So what we observe there? So idea is very clear. Whether it may be up counter or down counter, you need the flip-flops equal to number of bits. How many bit counter it is, you need those many flip-flops. How many bit counter it is, you need those many flip-flops. After those many flip-flops, you have to think of what clock is made common, reset is brought out. We have to think of what kind of inputs we would be applying to J and K of these three flip-flops. So now we should start looking at the down counter. We look at Q0. What is Q0? Q0, even in our down counter, it always toggles. 1 to 0, 0 to 1. 1 to 0, 0 to 1. So if a question is asked, design 1 bit up counter or 1 bit down counter, since there are only two states, up is same as down. So that's what I think once in some lecture I told that 1, 2 and many are different. 1 is separate, 2 is a different class, and then many. 3 onwards become many. So 2 is having a special significance. So 1 bit up counter and 1 bit down counter are same. So you find that Q0 always toggles. Next, in every next state you find that the Q0 is toggling. Therefore, what we do, we have same logic for, so when a flip-flop toggles, when both inputs are 1, 1, when both inputs are 1, 1, flip-flop toggles. So 1 and 1. So J is 1 and K is 1 for flip-flop number 0. For flip-flop number 0, J is 1 and K is 1. Then next is you look at Q1. You look at Q1. So at Q1, what we find? Q1 continues. 1, 1. Q1 toggles. Q1 continues. Q1 toggles. Q1 continues. So you look at Q1 and change in Q1 or maintaining last state. So it continues. You look at Q0. So for the action of either continuation or toggling of Q1, you look at Q0. So Q1 continues when Q0 is 1. Q1 toggles, Q0 is 0. Q1 continues, Q0 is 1. Q1 toggles, Q0 is 0. So very simple, exactly reverse of up counter. See, this is same for down and up counter. Whereas for flip-flop number 1, in case of up counter, flip-flop number 1 was toggling when output of flip-flop number 0 was 1, and when output was 0, it was maintaining. So what we have done, we have connected Q0, we have connected Q0 to J1 and K1. Here what will you connect? Here when Q0 is 0, you want it to toggle, and when Q0 is 1, you want it to maintain state. So you will connect Q0, you will invert Q0 and connect Q0 bar. You will connect Q0 bar to J1 and K1, and there is no need of inverting. There is no need of any NOT gate because already you have with you. Already you have. Already the Q bar is available with you. This is flip-flop number 0. Q0 bar is connected to J1 and K1. Q0 bar is connected to J1 and K1. Now next, what about Q2? Q2 continues the state, and when Q2 toggles, Q1, Q0 are 0, 0. It toggles. So you look at this 0, 0 and this toggling. This 0, 0 and this toggling. And at all other cases, continue, 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 continue. So continue, 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 other than 0, 0, continue, 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 continue. These are other than 0, 0, and at 0, 0 toggles. So when Q1 is 0 and Q0 is 0, toggling takes place. Q1 0 means Q1 bar 1, Q0 0 means Q0 bar 1. So I, instead of connecting ANDing Q1 and Q0, I AND Q1 bar and Q0 bar. So it is, both are not Q1 dot Q0 bar, Q1 bar, remember it is very De Morgan's theorem, I think it is a homework now. So Q1 bar and Q0 bar. So inputs J2 and K2 are Q1 bar and Q0 bar. Inputs J2 and K2 are Q1 bar and Q0 bar. This would be a down counter. This will be a down counter. So in general we discussed an up counter, a down counter for n number of bits. These are called as binary counters because they count from all zeros to all ones if it is up counter, and from all ones to all zeros in the given sequence if it is a down counter. Now decimal is having a very important significance because decimal number system was already in existence before the all binary digit thing started. So we want something to be counted in equal to decimal manner. So the counter should count from 0, 0, 0, 0, 0, 0, 0, 1 to 9, and after 9 it should become 0, 0, 0, 0 again. So directly we go for designing a decade counter. Now what is the difference in this counter? A decade counter is having how many states? A decade counter is having 10 states. Using 4 bits, how many states are possible? 16 states are possible. So when we design a decade up counter and designing decade down counter is all quite interesting. So what we are doing, out of 16 possible states, we want the counter to run not in all states but only in few states. So some further states should not be there. So we can, this is not a binary counter but it is called as mod and that count. So generally the counters are, if it is n bit counter, it is having 2 raised to n states. So a 2 bit count, 1 bit counter is having 2 states, mod 2 counter. A 2 bit counter is having 4 states, mod 4 counter. A 3 bit counter is having 8 states, mod 8 counter. Now if I want a counter to count less, so I will take an example and we can go through. So we can directly take an example of mod 10, but we start with basics. It is a mod 3 counter. So a mod 3 counter is a 2 bit. Once the theme is explained, we can go very easily. A mod 3 counter, we should start from basic. Mod 3 counter is what? It is having 2 bits Q1 and Q0. We are designing mod 3 up counter. 0 0, next state is 0 1, next state is 1 0, 0 0 0 1 1 0. The counter is over now. Next state is 0 0, then 0 1 and so on. It should count in this way: 0 0 0 1 1 0 0 0, 0 0 0 0 0 1 1 0 0 0. Now it is having 2 bits, so it will I will rub it out. We will be needing 2 flip-flops. We will be needing 2 flip-flops. So using 2 flip-flops, we need to use 2 flip-flops. Q1, Q0, J, K, J, K. Now, clock and reset of all is made common. Being a synchronous counter, clock and reset of all is made common and available outside as a clock for the counter, reset for the counter, so that I don't show. So what we show in the diagram is JK and Q. JK and Q, and obviously Q bar is also available. Q bar is also available. And this Q will come as externally. Q bar also available. What will come out externally? It will be having 2 bits. Obviously clock and reset that I am not showing. So what I should get? Q1, Q0 I should get 0 0 0 1 0 and 0 0. So now we put a pause. We take a break. All should think how this design can be done. And immediately in the next session, after this 2-minute break, we can continue for the discussing the design of this. So I expect that everybody should try to think. So designing is what? Designing is what? This is J0. This is flip-flop number 0, flip-flop number 1. So what should be J0, K0, J1 and K1. So J and K inputs of the flip-flop. What you are going to connect to the inputs, that you need to find out. Once you are able to write that, connection can be easily done. So deciding what should be J0, what should be K0, what should be J1, what should be K1. Once we are able to decide that, it is as good as our design of the flip-flop, design of the counter is over. I think everybody should attempt. We should take a break, and immediately after 2 minutes you can go to the next video session. Thank you.